Hello, today's presentation is about 3D chips and transistors and their advantages over 2D technologies. Uh, During this presentation, we'll cover several topics like why do we need 3D transistors and chips in the first place, what are FinFETs and 3D transistors and their advantages. Um, and we will also compare 3D integrated circuits with 2D technologies, and lastly, present some modern 3D chips that are manufactured by the leading semiconductor companies. So we are used to the idea that computer performance improves every year. In fact, the process is so predictable, it even has a name, Moore's Law. The idea is that the number of transistors you can etch onto a silicon wafer doubles roughly every 2 years, leading to vast improvements in microprocessor performance over time. When Gordon Moore came up with the concept in the 1960s, he thought it might run for a decade before puttering out. But incredibly, it continued for another 50 years, permitting the smartphone revolution and all the baggage that came with it. Now, the 2D silicon technology is bumping up against the laws of physics, and engineers can make features on their chips much smaller than about 5 nanometers without running into quantum strangeness. The problem with making chip features too small is that it allows electrons to hop from one part of the circuit to another, even if there is a resistor material in between. And that means that chips can't carry out their functions properly and heat up. The main solution seems to be 3D integration, or making processor features three-dimensional. How about 3D transistors? 3D power scaling is very different from the way 3D semiconductor packages are built today. The latter approach relies on stacking multiple 2D dies into three-dimensional packages using through silicon vias, TSVs, to integrate the individual devices. The technology is being used to construct 3D image sensors and 3D DRAM packages like the hybrid memory cube, HMC, and high bandwidth memory, HBM. Challenges include aligning the layers correctly and dealing with the added costs associated with constructing a device from multiple dies. Using 3D power scaling avoids those pitfalls, since the transistors are vertically oriented and laid down on top of each in a silicon manufacturing process. Such technology is already being employed to create 3D NAND flash. NAND technology has already become extremely difficult to scale below 20 nanometers or so, and now requires heroic error correction schemes to deal with endurance and data corruption issues. Now I will talk more in details about FinFET. The gate wraps around the fin, as we can see on the image. The current is controlled by using a gate on each of the 3 sides of the fin, 2 on each side and across the top, and rather than just one on top, as is the case with 2D planar transistors. The additional control enables as much transistor current flowing as possible when the transistor is in on state, and that increases performance, and as close to zero as possible when it is in the off state. That is also for minimizing power. That enables the transistor to switch very quickly between the 2 states. Does this mean faster chips? Of course, but also more power efficient designs. And the biggest challenge nowadays is going forward, but not just with speed, but also power efficiency. The 3D transistors enable chips to operate at lower voltage with lower leakage, providing both improved performance and energy efficiency compared to previous chips. Now I will discuss 3D integrated circuits. 3D ICs are integrated circuits that incorporate 2 or more layers of circuitry in a single package. The layers are interconnected vertically as well as horizontally. The multi-layer chips are usually created by manufacturing separate layers and then stacking and thinning them. Vertical electrical connections, TSVs, purge the underlying silicon substrates to connect the circuitry on the different layers. Stacking can be done die on die, die on wafer, wafer on wafer, or in combination. The thickness of the layers, the diameter of the TSV, and the number and density of the TSVs are important factors in the performance of the finished 3D IC. Compared to this traditional 2D architecture, 3D ICs provide several significant advantages. First is the footprint. Obviously, stacking multiple dies atop one another produces a chip that takes up less space than if those dies were side by side. If the layers are aggressively thin, a multi-layer 3D IC is actually no thicker than a traditional 2D chip. The tiny size of the 3D ICs is extremely valuable in miniaturizing devices such as cell phones and IoT application. Now, speed. Dice stacked in a 3D chip are much closer together than chips on a circuit board. The shorter distances allow electronic signals to travel more quickly from one component to another. 3D stacked devices have shown as much as 5 times improvement over comparable 2D solutions. And now, Nika will continue the presentation.
Thank you, Mari. Now I will go on about the power. Shorter connections automatically require less power, but 3D ICs have another power-saving trick. When electronic signal travels from a chip to another, it passes through special circuitry that screens out any accidental electronic discharges, ESDs. These ESD filters consume energy. Signals that travel from one layer to another layer within 3D ICs do not require ESD checks. Tests have been as much as 90% reduction in the power consumption. When we talk about power, we also can't forget about heterogeneous integration, because the layers in a 3D IC are manufactured separately, they can be built differently. This is more important than it might seem. The process in which a die is built affects the behavior of the components on the die. One process makes better capacitors, another makes faster transistors, and etc. Even more interesting, the layers may be built at different process nodes that the electronic components may differ in size. This affects the cost, complexity, and performance of each layer. It is even possible to stack layers that are built of different materials. All of those possibilities mean that a 3D IC can combine the best of each process nodes. They substrate without compromising some components and accommodate others. In fact, a multi-die stack can contain combinations that are flatly impossible to achieve on a 2D chip. Sorry. Now, let's question ourselves. Are 3D chips really the future of IC design? Successful companies like Intel, TSMC, AMD, Samsung has started manufacturing those chips. As we know, TSMC has been the biggest chip manufacturer right now in the world. So as we know, TSMC has been working on its 3D fabric that is making both front and back end of microchips 3D. I will concentrate on SoCs now, how they're built and how they're mostly done. This is a service platform that provides innovative front-end 3D Intel chips, 3D IC stackings, technologies that are for reintegration of chiplets partitioned from system of chips, SoCs. The resulting integrated chip outperforms the original SoC in system performance. It also affords the flexibility to integrate additional system functionalities. It meets even increasing compute bandwidth and latency requirements in cloud, network, and edge applications. It supports both chip on wafer and wafer on wafer schemes. The dual scheme provides superb design flexibility in mixing and matching different chip functions, size, and technology nodes. A 3D IC system interconnection is vertical instead of horizontal, like 2D and 2.5D. 3D connection is significantly shorter than the 2D. TSMC SoICs is the company's IC inter-chip stacking technology that allows integration of chiplets with multi-layer, multi-chip sizes, and multi-functions. System on a chip SoC can be partitioned into chiplets which varying functions. The chiplets can be manufactured with tailored technologies for optimizing performance, cost, and time to market. TSMC SoICs can get tightly integrates the different chiplets into a new chip. It is an innovative bonding scheme, offers intrinsically exceptional bonding pitch and scalability that bring chiplets closer together to enable faster and shorter connections. So what would I say are the main advantages? I would mainly say that bonding density, speed, bandwidth, power consumption, flexibility. Now I would love to talk about something a little bit. As we know, the new technology called X-Cube was tested on and proven in a 7-nanometer test chip, which stacked SRAM on the top of logic chips. The result was smaller footprint of a shorter signal path, meaning faster signal propagation and less power consumption. X-Cube is also in advanced nodes, both 7-nanometer and 5-nanometer. This advance from Samsung addresses several trends in chip design, facing the end of Mariam's law, increasing chip functionality and addressing the difficulties of system on chip. One of the major challenges in SoC design is the fact that integrating more functional blocks onto one chip requires significantly more chip area, but the combination of greater chip area and subsequently smaller node size leads to a huge rise in interconnection parasitics. Longer wire lengths must be used to connect different blocks in a physically larger chip, which increases interconnection endurance. To allow chips to continually expand in size while overcoming this aforementioned issues, designers have turned the 3D IC technology to 3D IC technologies. 3D IC ICs are unique in that they physically stack silicon wafers on dies and top of each other, most notably decreasing the interconnect lengths compared to the helps elevate parasitic impedances in the interconnect, which is turned to allow for decreased propagation delay. This was all. Thank you very much for your attention, and goodbye.